Good morning here, Algebra 2 Extended, Lesson 3.3 here. We're talking about quadratic functions in zeros and what they look like and kind of how many there can be. So our essential ideas are listed there on the top like they are in your note sheet. And before we get rolling, I'd like you to hit pause and I would like you to complete these 3 warm-up problems, see if you got them right, converting to standard form and then writing a quadratic function through the given points. Hopefully you completed these on your own. The first one, basically what we do is we just double distribute. I always hold that negative sign outside and distribute it at the very end. Should have gotten negative 2x squared plus 7x plus 15. If not, track your work in mind. B, next big thing, most people say x minus 3 quantity squared is x squared plus 9. Big mistake. That means x minus 3 times x minus 3, which means, again, I have to double distribute from here down. And that 5, notice that 5 is the very last thing I'm going to do. Very last thing I'm going to do when I add that in there. After I double distribute, I have to distribute that 2 yet. Standard form for B should be 2x squared minus 24x plus 23. And part C, because they gave me the vertex, I am going to use vertex form to write this equation. And remember, the vertex is at h comma k, or opposite of h, comma same as k. And then they gave me an x and a y, so I can utilize all 4 variables in my equation there and just find what a is. So I plug them in, come through, find out a is negative 1/4. Then all I got to do is grab that a value, plug it in, and remember that's x minus negative 4. That's why it's x plus 4 quantity squared minus 3. So hopefully you did all right on those. And we're moving along here, identifying the number of zeros. Okay, think back to Algebra 1. X-intercepts of a quadratic equation. They have many names, okay? They're known as zeros and roots of the quadratic. They're also known as graphic solutions, okay? Algebraically, what they are, the x values that when substituted into the quadratic result in a value of f of x equaling 0. That's why we can use a zero product property when we factor, okay? So algebraically, the solutions are the equation equal to 0. Graphically, the zeros are where the parabola intersects the x-axis. So think about that. How many ways can you graph a parabola, either concave up or concave down? How many different ways can it hit the x-axis? Well, does it have to hit it? No, it does not. Does it have to, if it hits it at the vertex, maybe once, and potentially it could also be 2 times. Okay, so we're looking at how many times could it? We're kind of thinking 0, 1, or 2 times. Okay, well, usually in class we would go through and have you graph these next 6 functions in an Inspire. You can go ahead and do these on Desmos if you want to hit pause and go through. What I've done is I've graphed them on my Inspire and I pasted the graphs of them in there. And as I'm looking here at numbers 1, 2, and 3, okay, first thing I did is I also labeled where my vertex is. So number 1, if you found the vertex in standard form, find it up there at 1.5, 9.5. It's concave down. Looks like I intersect twice for 2 zeros. Number 2, when I graph it, there's my vertex at 2, 1. Opens up. I have 0 zeros. And number 3, when I'm looking at 2x squared plus 12x plus 18, I can see here's my vertex, therefore I'm touching it 1 time. And what we're going to do is we're going to take a little gander at these next 4. And when I graph these next 4, we're just kind of predicting. And when I'm looking here, well, it looks like number 4 has 1 0. Appears number 2 has one there, it has one there, so it has 2. And let me come back, there's my 1 because it was vertex. And here I have 0 zeros because I do not touch the x-axis anywhere. So does our prediction about the possible number of times a parabola can cross the x-axis seem to hold true? Yep, sure does. Okay, and again, we learned that, or you learned that, back in Algebra 1. Okay, Well, when we're identifying zeros, I found some people were doing this on the last chapter's review assignment where we said the x-intercepts are between two values, where we'll call them a tweener at the time. The reason we call them a tweener was because we haven't really talked about the quadratic formula, and this formula solves any quadratic equation that is set equal to 0. Okay, so bottom line, when should I use the quadratic formula? Well, number one on the previous page had two zeros, but they weren't nice values. Let's just squirrel back here once. Let's just take a little gander at that. These are not nice values because they're decimals. They're the tweeners that I was talking about. Okay, and like number three I know is going to factor because it's got a really nice intercept. And actually, that's probably going to factor for me as well because they're actually pretty nice values, 1.5 and 9.5. So that would factor, but they're not really exactly what we call nice values. Nice values are whole numbers. So on the previous page, we're going to go through that. Well, actually, no, I'm sorry. That was my vertex that I was talking about, 1.5, 9.5, not my x-intercepts. And if I try to factor this little rat, it doesn't factor. Okay? Does not factor. I can try, and I can try. I will exhaust all of them. So what we need to do is we need to use a quadratic formula up there. And remember, a, when I think of f of x, equals ax squared plus bx plus c. I just wrote it a little bit bigger so I can identify a, b, and c. So the a value is -2. My b value would be 6. And my c value would be 5. Just like I would think everybody's going to say, well, let's ram this little bugger through the quadratic formula. So what I should do is I should think x equals, well, the opposite of b is going to be -6 plus or minus the square root of b squared is going to be 6 squared minus 4 times a times c, all divided by 2 times a. Okay? Well, what does that equal? Well, that equals -6 plus or minus the square root of. Everybody tries to do these a little too fast in their head, and they drop signs, especially over here in this part. But 6 squared is 36. And when I see a negative times a positive, I know that's going to be a positive number. And 8 times 5 just gives me 40. And that's going to be over -4. And simplified a little bit more, I get -6 plus or minus the square root of 36 and 40 is 76 over -4. Well, we can see right here, okay, anybody know what the square root of 76 is? Me either. That's why it doesn't factor, because that underneath that square root, that is not a perfect square. If that were a perfect square, this little bugger would factor, but it's not. And notice there's 2 because there's a plus and a minus. So I'm looking at x equals -6 plus or minus the square root of 76 over -4. Well, that is going to be approximately equal to, so when I take x equals -6 plus or minus square root of 76 divided by -4, and I let my fingers do the walking through my calculator, I'm going to approximate these. This is approximately equal to -0.6794. There's one, and the other one is x equals -6 minus the square root of 76 divided by -4. And that, when I type in my calculator, is approximately equal to 3.6794. Okay, so those are my approximated. Now, these are irrational numbers because those decimals keep on going and going and going. Well, what are we going to do with the quadratic formula today is really what we're going to do is a value inside the square root, right here, b squared minus 4ac. That is called the discriminant, and it holds a lot of very important things for us in a quadratic equation. We're going to explore this value in the 6 functions that we graphed, okay? So I can tell if I look back, and you can look in your note sheet there, number 1 had 2 zeros. Well, if it had 2 zeros, what did our discriminant have for us? Well, we just did that one above, okay? That's where we took our 6 squared minus 4 times negative 2 times 5. Well, that gave us 36 plus 40, and that gave us 76. Well, when I got the number 76, I had 2 solutions, or 2 zeros. Number 2, when I look at that graph, I didn't have any x-intercepts. Well, what did that discriminant look like? Well, when I'm looking at b squared, I got to take negative 4 squared minus 4 times a times c. Well, that gives me 16 minus 20. 16 minus 20, that gave me negative 4. Okay? And number 3 had 1 zero. And when I take the discriminant here, I take 12 squared minus 4 times a times c. And that's going to give me 144 negative, positive, minus 8 times 18 is 144, and that gives me 0, okay? So I'm kind of looking at, I'm comparing my number of zeros with my discriminant value here, okay? We're going to do these next 3 that I got here yet. Number 4 had 1 zero, so that discriminant was 8 squared minus 4 times negative 1 times negative 16. Well, that gives me times 8 is 64. Negative times a negative times a negative is going to be a negative. 4 times 16 is 64. And that gives me 0. So 1, 0 correlated here again. And when I look back at number 2, there were 2 zeros. Discriminant, negative 4 squared minus 4 times a, which is a half, times c, which is negative 5. That gives me 16 plus 4 times a half is 2 times 5 is 10. That should give me 26. And when I had 2 values, or 2 zeros, I had 26. Last time I had 76. And number 6, I had 0 numbers of zeros, and we're going to type that in and say 5 squared minus 4 times a times c. That gives me 25. Negative times a negative is positive times another negative, so this is going to be minus 12 times 4. It's going to give me 48. 25 minus 48 gives me negative 23. Okay, so 0 zeros gives me negative 23. So what we need to do is we want to formulate a conclusion regarding the value of the discriminant, how it relates to the number of zeros. Well, if I look back, and 2 of them. Well, when I got 2 of them, I had 26. In the previous screen, when I had 2 of them, I had 76. Must be something that they end with a 6, right? No, it's not that. What my first one is if b squared minus 4ac is greater than 0. All that means, greater than 0 means it's a positive number. So if my discriminant has a positive number, there are 2 zeros or real solutions. Well, when I went to see what happened when it was less than 0, well, I had negative 23. Thinking back, I had 0. Previous screen, I had negative 4. I had 0. So what does that mean? Well, that means that if b squared minus 4ac is less than 0, meaning all that means is it's a negative number. If my discriminant is a negative number, there are no zeros or real solutions. And if my discriminant equals 0, okay, meaning the number is not positive or negative, it's just straight up 0, there is one real solution, and that is where your vertex is actually your x-intercept, okay? And just wanted to see, I don't have any more there. So really super important thing here. Really important. Big idea here. Big idea, if you forgot. Okay, big idea, get that in your notes, okay? So then we're going to come here. What we're going to do is we are going to use the discriminant, okay? And what we're going to do is we're not going to use it. We're going to use a graph, and we're going to predict what the discriminant would have been, okay? Almost all of these, 7 through 11, they're way easiest to do with a graph. Thinking, okay, well, if I had a vertex at -2, -5, that's 1, 2, 1, 2, 3, 4, 5. Here's my vertex. And if A is greater than 0, that means I'm concave up. Okay? Then how many zeros will I have? I will have 2 zeros. Well, what does that mean? Okay, what conclusion can I make on the discriminant? Is it going to be positive, negative, 0? Well, that means b squared minus 4ac, if I had 2 zeros, has to be a positive number. It's got to be positive, okay? And when I go on to number 8, and all I got to do is I just got to picture a lot of these guys. That's all you're really doing. So if I have a vertex at 3, 2, well, that's 1, 2, 3, 1, 2. So here's my vertex. And I have a y-intercept of 5. Okay, so that's 1, 2, 3, 4, 5. If I have a y-intercept there, if this is my vertex, this thing has to be concave up, doesn't it? It has to be going up like this, which means I have 0 zeros, which means b squared minus 4ac, the discriminant, is less than 0 or negative. Okay? And we can tell all this just by looking at the graph of a function. Okay? And I got another one here. I got a vertex at 2, 0. So there's my vertex. And it's going to go through the point 4, -8. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. So it's going through this point. Well, it's got to be concave down. If this is a vertex, it's coming down. Coming down. I don't know if it's the right graph. I know the vertex and that point are right. Okay, so what does that mean? 1, 0, which means b squared minus 4ac equals 0, which means the discriminant is 0. Okay, and also let me expound on this just a little bit further. And they're not just zeros. Okay. They're not just zeros. They're also called real solutions. Real solutions. And a real solution is an x-intercept, okay? One real solution. So if there are no zeros, then there are no real solutions because I had no x-intercepts, okay? So, and I can just find those just by graphing a few points, making a rough sketch of a graph that I know. Just by looking at that thing, I can say, hey, this thing has so many zeros. Now, number 10 is a very difficult one, okay? Number 10, you got to really think hard. So that's why I have graph paper on here. And I'm going to go -2, 1, 2, 3. So I'm going through this point. I'm going through 1, 2, 3, 4, 1, 2, 3. And I'm going through 5, 5, okay? Oop, that's 5, 4. Got to get that up a little bit further. So bottom line, I can see this thing is going to be concave up. But the question is does it hit it? Does it not hit it? Or does it hit it twice? Okay? And a lot of times the automatic default here is not enough information. I'm getting all those off. But if I can get you to think here now, sorry, pretty early in the morning, okay? I actually have in the notes, the filled out notes online, I have a real long explanation of this in there with a graph. But let me think about excuse me, let me think about this. Well, I know between 2 points on here, I can tell automatically this is going to be my axis of symmetry. That has to be my axis of symmetry because these 2 points at the same y value, they're equidistant across. So that has, my axis of symmetry has to be 1, okay? So knowing that, whenever we knew where our vertex was, think about it, we always used our over 1, up or down 1, or we went over 2, we went up or down 4, we went over 3, we went up or down 9. And I can extend this 1, 4, 9 process. All I got to do is if I go over 4, I would technically go up or down 16 units. Now, these all come from the parent graph, y equals x squared. Well, what I'm thinking here, I know my vertex is on this red line. So I'm 1, 2, 3 away. I'm over 3, up typically 9. This other one's over 4. Typically, I would be up 16. Well, I can use the a value really simple here with respect to my axis of symmetry. Okay, my a value is going to equal my actual distance and what I mean is actual distance, the actual distance between over 3 and over 4, usually I'd go over 3 up 9, over 4 up 16. The actual distance between these 2 points is 7 units. Okay, so if I take my actual, or my actual distance, my actual distance vertically is 2 units. So if I take my actual distance divided by expected distance, and this is where I expect it to be 7 units, I can see my a value is 2/7. Now, I can use that a value to work backwards because typically, if I went over 4 units, I would go up or down. In this case, I'm going down or up. I would go up my 16 times my a value of 2/7, which would give me 32/7, which is 4 and 4/7. So if I went backwards, I should be able to go down 4 and 4/7 and then go left 4 units to find my vertex. So if I went 1, 2, 3, 4, and 4/7 is a little under a half over 4, my vertex should be right about there. And I can use it on my other one too. Typically, if I go over 3 units, I would be going up or down 9 units times 2/7. Well, that's going to give me what? 18/7, which is equal to what's that going to be? 2 and 4/7, right? Whoa, that's a 7. 2 and 4/7. So if I went from this, I'm going to go down 1, 2, and 4/7, and I get back there. Sorry for the PA interruption there, but if you notice, I can go down. Whoa, I can go down these 2 and 4/7 to the left 3, or I can go down 4 and 4/7 to the left 4, and I can come right in there and I can find where that vertex is by taking that actual distance divided by expected distance gives me my a value, and then back that up. So I can see here's my vertex. So that means this little rascal would go like that, which means how many zeros would that particular one have? Well, notice these are just 3 random points we got on here at the same time too, but I think it's pretty obvious there are 0 zeros, which means b squared minus 4ac. If I don't have any zeros, that's got to be less than 0 or negative. Okay, now that was a tough one. And those tough ones, Sometimes graph paper works better than your own drawing of a scale graph. See, here's 3 rogue points. Before, in the first examples, they were giving me the vertex or whatever. Sometimes they'll give you x-intercept. So I'm going to go through these points. I'm going to go over 2, up 3, over 6, 2, 4, 6, up 3. And I'm going to go over 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Well, again, I don't need to think too hard on this one. And I do know that my axis of symmetry is going to be right here, perfectly between these 2 points. But I don't need to think about this 1, 4, 9 pattern in any way, shape, or form like I did in number 10, because it's obvious, hopefully, that the vertex has to be somewhere, and it's going to go down, and it's going to go down. I don't need to know precisely where it is, which means this is going to have 2 zeros, which means b squared minus 4ac is going to be greater than 0, meaning it is going to be positive. Okay? And that's basically what you're going to be doing in your work. Again, number 10's a tough one. I do have a nice separate sheet at the end of the note sheets, all worked out in color with a nice graph, and I tried to explain it in words really well for you. So other than that, have a great rest of your day. See you tomorrow.